Hello everyone, this is Professor DePaulo welcoming you back to Psych 220 Behavioral Statistics fully online. And this week we're going to be talking about the variability or measures of dispersion. So some of the overview for this week's topics include the purpose of measuring variability, defining the range and computing the range, which is relatively simple to do, understanding variance and standard deviation, which is a little bit more complicated, and calculating the SS, which is the sum of squared deviations about the mean, or usually is known as sum of squares, the variance, the standard deviation of the population, and doing the same thing for a sample, and then talking about the differences between computing the sample variance and sample standard deviation compared to computing the population variance and the population standard deviation. So variability is just the distance between scores in your data set, in the population, if you have access to the entire population, which is generally not the case, mainly in your sample. So how spread out are the scores in your sample? And the one way we can figure out how spread out the scores in your sample are is measuring the distance between each score and the mean. And that's what we're going to be doing when we're calculating variance and standard deviation. The purpose of measuring variability is to describe the distribution. So are we measuring something where everybody's scoring about the same, or are we measuring something where there's a lot of noise? So people are all over the place on whatever variable we're measuring, and that's going to make our life harder in terms of explaining the data set, and definitely in terms of doing the inferential statistical test that we're going to be calculating later in the course. So a lot of variability causes a lot of difficulties at times. And this allows us to sort of describe the distribution we're studying, whether it be the population or the sample. Usually the population is more spread out than the sample. Due to statistical laws, the sample has less variability than the population as a whole. But it gives us an idea of, what's going on with the measurement we're using. Uh, what is it really entailing as far as how people are being assessed? For instance, if I give an exam and there's a lot of variability, that tells me that some people are understanding things and other people are not understanding things, and we have to try to remedy that situation the best that we can. Whereas if I give the same exam, there's very low variability, that could be good or bad, right? I mean, it could be that everybody failed and there's low variability because everyone's scoring like 10, 20, 30 on the exam. That's not what I would want in a low variability situation. Or it could be the more preferred alternative that everyone did well. People were scoring 90s, 80s, and 70s, preferably 90s and 80s, right? That would be a good situation where there's low variability. So knowing how variable the distribution is tells us about the measure, tells us about the variable we're measuring. It also tells us whether or not we have a ceiling effect or a floor effect. That means the task is too easy or the task is too hard, and that's useful as well in terms of research. If you look at this figure, we have two distributions with different variabilities. So U.S. Men's height in inches is a lot less variable than U.S. men's weight in pounds. As you can see on the left, the average height for a male in this country is 70 inches, which is 5'10". And there's some variability, so you have some people that are taller and some people that are shorter, but it's kind of narrowly focused around the mean, which is 70. On the right, you see weight for U.S. adult men in the U.S., and there's so much variability here. I mean, the mean is 170, but you have a great deal of flux in this distribution. You have some people that are over 230, and you have some people that are really, underweight, under 110. And although you have most of the variability in the middle, it's spread out a lot more than height. And that's kind of obvious because genetics control height for the most part, right? I mean, I guess there can be environmental influences early in life, but there's certainly a lot more of the environmental influence on weight. I mean, weight is genetic to a degree, but it's also heavily environmental, and that's why you're seeing all of this spread, this wide amount of variability. And if we're doing research, we really don't want that, especially if we're looking for differences between two conditions. Ideally, we would want the variability to be smaller because that allows the actual magnitude of the difference to be expressed better when the variability is smaller than if it's larger. So there are pitfalls with large amounts of variability. We also don't want no variability either, because if you have no variability, you can't do any statistics. So you have to have some, but you don't, ideally you don't want an enormous amount of variability in your data set, your sample. Obviously, you really don't have access to the population. So the three main measures of variability that we're going to talk about, which you're very familiar with by now, I'm sure, are the range, which is kind of not that useful, the variance, which is a little bit more useful, although it's a squared term, and the standard deviation, which is the most useful of the three. And variance and standard deviation are always used in inferential stats, and so you're going to be seeing this again and again and again. As a result, you want to sort of get this down now, learn it now, and then because the future material is going to be building on this chapter especially. I mean, mean is important too, but mean is pretty easy to calculate. The variance and standard deviation take a little bit more work. So work hard, practice, do the online stuff, send me emails if there's a problem, come to office hours, and let's try to get this solidified moving forward. So the first topic is the range, which is not that important. I mean, it's useful for like a frequency distribution, like to know where the lowest intervals and the upper intervals are. It can help you if there are outliers, like extreme scores in either direction. Data entry errors can be picked up by the range. It's just the difference between the smallest and the largest value. And the way that I compute the range is always highest minus lowest. For the text, they talk about real limits. It basically amounts to highest minus lowest plus 1. So this whole idea of like, take the real limit, of the maximum, the upper real limit, or lower real limit of the minimum, well, that's just adding 1 to it. So my preferred method of calculating range, and I will specify this moving forward for the exam, is highest minus lowest. However, the text does talk about an alternative method for continuous data that is the highest score minus the lowest score plus 1. And that's what basically this formula is, where you see upper real limit. It's just high score minus low score plus 1. That's all it is. The range is not that important. I guess you can guess, make a guess about the standard deviation based on the range. So a crude guess of the standard deviation based on the range is that the standard deviation is 1/4 the range. That gets you something close to what it actually is. You're not going to get the exact number, obviously, doing this, but it gets you a ballpark figure. 1/4 the range is generally the standard deviation, around that number. But the range in terms of inferential stats is not used. It's purely a descriptive measure, and it's not that important. It doesn't give you that much information. It's useful for outliers, data entry errors, some other oddball data points, but that's about it. The most common and the most important measure of variability is the standard deviation, which is the average distance from each point in the data set or the sample to the mean. So it's the average distance from each point to the mean. The variance is just the square of the standard deviation. However, we cannot calculate the standard deviation directly before we calculate the variance. So we always must calculate variance first, and then once we have the variance, we can easily take the square root and then calculate the standard deviation. So they're not different. Variance is a square term, and the standard deviation is a linear term, right? When we think of linear, we think of actual distance, right, on a number line. Distance on a number line is a linear measure. So variability, the variance itself, is not that useful for describing things, because we don't like to talk about, well, the variance is 10, so that's 10 squared units. What is a squared unit? We don't really have a concept of squared units. So that's why we talk in terms of describing the data, we talk in terms of the standard deviation. But you must calculate the variance to then get the standard deviation because of certain principles inherent in calculating the variance, right? And we'll talk about that shortly. The calculation does differ for populations and samples. For populations, it's a pretty basic calculation. For a sample, there has to be a correction that's used, and I'll explain what the correction is later on in the module. So to calculate the standard deviation, if it's the average distance from each point to the mean, it's pretty obvious that we would just subtract the mean from each data point, from each score. And that creates what's called a deviation score. So if we're dealing with a population, each individual score here is x, and the population mean is mu. That little mu curve that you see here, x minus mu. So each score in the population is x, and mu is the population mean. And so it's x minus mu gives you the deviation score. And so if it's the average, so if standard deviation is the average distance from each score to the mean, it would just be simple to calculate the deviation scores, right? And then divide by the number of scores you have in your population or your sample, whatever you're calculating it in. But there's a problem with this. Well, the big problem with doing the standard deviation this way is that if you add up all the deviation scores, all the x minus mu's in your population, you're going to always get 0. So then if you divide 0 by the number of scores you have, you're going to always have 0. So therefore, the standard deviation would always be 0. And that makes no sense at all. And the reason is because these deviation scores always must add to 0, must sum to 0. Because the mean is the balancing point. You saw the graphics of the mean and like the fulcrum, the mean is the fulcrum and it balances the left and the right side. Well, what happens when you balance the left and the right side? Whatever's on the left and whatever's on the right all cancel each other out and you get 0. So the sum of the deviation scores, the sum of the x minus mu's, will always be 0. So you can't find the standard deviation by just adding up all these deviation scores and dividing by n because you'll always get 0. So you need to find an alternative method, and that's how we get to the variance. So the alternative method is you take those deviation scores that you just calculated, but you don't add them up because if you add them up, you get 0. Before you add them up, square all those deviation scores. So once you square those deviation scores, guess what? You get rid of the negatives. And therefore you don't have this canceling out. You don't have it adding up to 0 anymore. So these deviation scores become squared deviation scores. And now if you want to find the average of those squared deviation scores, you sum up those squared deviations and you divide by the number of scores. So if I add up all the squared deviation scores and divide by the number of total scores, I will have the population variance. So the population variance is first, compute the deviation scores, which is x minus mu. Step 2, square those deviation scores. Step 3, add up those squared deviation scores. And step 4, divide the sum of those squared deviation scores by the number of total scores you have, your n. And that will give you the variance. When I add up all those squared deviation scores, I have what is known as the sum of squares. So the SS. You're going to see that term over and over again, SS. Those are the sum of the squared deviation scores. And that value will always be greater than 0 unless all the scores are the same. I mean, if every score is the same in the distribution, then it will be 0. But if that's not the case, it will always be a positive number. It cannot be negative because you're squaring all the deviation scores, and by squaring them, you're making them positive. So you can never have a negative variance as far as what we're doing in this class. You can never get a negative value for the variance, and therefore you can never get a negative value for the standard deviation. It has to be 0 or positive at all times. And this is kind of what I had just mentioned. You add up the squared deviation scores, you divide by n, and that gets you the variance. And then once you have the variance, you could just take the square root of the variance, and that will give you the standard deviation. And like I previously mentioned, this will always be positive. The variance is positive, and therefore the square root of the variance will be positive. Or it could be 0 in the rare situation that every score in the distribution is exactly the same. Then it would be 0. But it has to be non-negative. Realistically speaking, it's never going to be 0. I mean, you're never going to have a situation in real life where the variance will be 0 because not everyone's going to score the same on any measurement. I mean, there's always going to be some variability. It's never going to, I've never seen a situation where it was 0. I guess technically, if I gave you an impossible exam that did not measure statistical ability, let's say I gave you an exam on like some advanced physics topic that no one's ever been exposed to before, and asked you to give me an essay response, and I just gave you 0 on everything because you don't know what you're doing, right? Obviously, you wouldn't know what you're doing if you took an exam on some advanced physics topic that you never, or chemistry topic that you never took before. Then you'd all score 0, and the standard deviation would be 0, the variance would be 0. But that's not a realistic situation in any context that you're going to encounter ever. So theoretically, it's possible to have 0, but it's highly unlikely. Almost, I've never seen it in real life. So here are the steps to calculate the variance and standard deviation. So first, find the deviation scores. Don't add those deviation scores up yet. Calculate them, then square them. Square those deviation scores. Then find the average of those squared deviation scores by dividing by the total sample size or the population size. That gives you the variance, and then take the square root of the variance to get the standard deviation. And the standard deviation will be the average distance between each point in the distribution and the mean. And then you're done. So it's not that difficult. There are situations where there's better ways to compute it by hand, but the concept is the most important point. It's the average of the squared deviations from the mean. That's the variance. And since the variance is a squared term, it's in squared units, to make it more understandable, we need to take the square root of it to get the average distance between each point in the mean, which is known as the standard deviation. Here's just an example of a distribution. You see the mean here of the population is 6. And there's only 5 scores here, right? The maximum distance between each point in the mean is 5. That's the biggest difference. That's the biggest deviation score here. So 6 is the mean and 1 is the score. So if I were to compute the deviation score here, it would be 1 minus 6, which would be negative 5. So that's the largest distance between any single score here and the mean is 5. The deviation score would be technically negative 5, which means 5 units to the left. And you see that depicted in the graph here. The smallest difference between any point and the mean is 1. It's either between 5 and the mean of 6, or between 7 and the mean of 6. They're both 1 unit apart from the mean. So we have the highest difference, which is 5, and the smallest difference, which is 1. We know that the standard deviation must fall between those two values. The standard deviation must be between 1 and 5. And in this situation, you can actually calculate it. You find the deviation scores. You do 1 minus 6 squared. You do 5 minus 6 squared, 7 minus 6 squared, 8 minus 6 squared, and 9 minus 6 squared. Then you add up all those squared deviation scores, divide by 5, and that will give you the standard deviation. And you can do that on your own. It's simple enough because you're dealing with whole numbers here. So for the population, as I mentioned, the variance is the sum of squared deviations about the mean divided by the number of scores. And there's two different formulas for computing the sum of squares. What we're talking about at the beginning of this chapter is what's called the definitional formula, which means it's basically how you derive it, the academic way of understanding how the variance and standard deviation is derived by subtracting taking each score in the distribution and subtracting the mean from it, and then squaring those deviation scores. That is basically the concept of deriving the variance and standard deviation. There's also a shortcut, what we call the computational formula, to calculate the variance, which is a good way to do it if you have fractional means. So if you have a decimal in your mean, for your mean, you have a decimal point, you want to use the computational formula because it's going to get rid of all the decimals. If you use the deviation score method, you're going to have, 7 minus 5.33, and then you have to calculate deviation score, which is 1.667, and then you have to square that. And now you're squaring all these decimals, which gives you more decimals, and it makes your life harder to compute it. You need a calculator. It can be done. It's just more work. So whenever the mean has a decimal point involved, it's not a whole number, it's best to use this computational method that I'm going to show you how to calculate the variance and standard deviation. So here's the comparison. We've been talking about the definitional formula, where you find each score, subtract the mean, square those deviation scores, and then sum up the squared deviations to get you the sum of squares. And you see that at the bottom left here, you have sum of x minus mu squared. That's just the sum of the squared deviation scores. The deviation score is x minus mu, each score minus the mean of the population. As I said before, if the mean's a whole number, that's easy. You can do it that way pretty quickly. If the mean is fractional or has a decimal point involved, now you're going to be squaring all these decimal values. It's going to be messy, especially with a large data set. I've done it both. Obviously, I've done it all the ways possible. And this is a very messy method when you have a fractional mean. When you have decimal point involved, you want to use the computational formula because it's much easier. And you can use it anyway. You can use it anytime you compute it. You'll get the same answer with either formula if you do it correctly. So if you think the computational formula is just easier, and personally I think it's just easier, you could do it all the time. And you don't have to worry about decimals here. So what you have to do for the computational formula is you have to first compute x squared values. So take each score, square each score. So you're going to have an x column of x's, and you're going to have a column of x squared scores. You're going to add up both columns. You're going to sum up the x column, which are your raw scores. You're going to sum up your x squared column, which is the squared scores. And now you're going to plug it into this formula here. So when you sum up all the squared x's, that's going to be your first term, where you see sum of x squared. You're going to plug in the sum of the column that you just made for the x squares. Minus, now you see this is where you have to be careful. This is a little trickier. Sum of x. Now remember order of operations, your PEMDAs. Please excuse my dear Aunt Sally. So parentheses, exponents, multiplication and division, addition and subtraction, right? That's the order of operations. So whatever you see in the parentheses has to be done first. So it says sum of x here in parentheses. That means you're going to sum up your X column of scores. And the best way to do this is list the scores in a column and then sum up the column. Same thing you did with the X squared. You listed the scores of the column and sum up the column. Sum up that X column, square it, square that sum. So don't square each score first, square the sum. So sum up the column X first, square that sum, that total, and then divide that total by the total sample size, which is capital N. That's every score. So how many scores you have, that's going to be your N there. And when you do that, you're going to get the sum of squares for the computational method. Obviously, you want to be careful that you're using the right method. So the sum of squares does not equal the sum of X squared. That's wrong. Use the formula. The same thing, you see the second line here, the sum of squares does not equal the sum of X quantity squared. And obviously the sum of X squared does not equal the sum of X quantity squared. You can't just kind of move the exponent over. They're not the same. So make sure you don't screw up that third one where you see sum of X squared and the sum of X in parentheses squared. That's where students make mistakes. Don't make a mistake there. On the left, you square each score and then add up the squared scores. On the right, you sum up each score and then square the sum of all the x's. And those are completely different, give you different calculations. So the variance of the population is simply the sum of squares, which we just mentioned, divided by the total sample size. And the standard deviation is just the square root of that. And if you see the population variance, it's going to be notated as the Greek letter sigma squared. So you see that little circle with a little tail line on the top, sigma? That's lowercase sigma squared. That means the population variance. If you don't see the squared and you just see sigma, then you know it means the population standard deviation. So those are parameters because they are measuring the population, and parameters are written in the Greek letters. If it's a sample, you're not going to see that. You're not going to see sigma, you're going to see S. So you're not going to see the Greek letter. So keep that in mind. Now, calculating variance and standard deviation is all about performing inferential statistics in the long run. So it's good to describe your sample, but it's more important to take the variability in your sample and try to extrapolate it to the population. Now, samples have less variability than the population because when you keep adding people together in your sample, there's a higher probability that the people you're selecting from the sample come towards the middle of the distribution. So whatever population you're sampling from, there's a higher probability that when you put these people together, they're going to have a value that's closer to what the mean is representing in the population. So samples have less variability. More so, the bigger your sample, the less variability you're going to have. And there's a law for this. It's called central limit theory that we're hopefully going to get into later on, although I'm not sure how much I'm going to go into it. It basically says that your sample variance is always going to be smaller than the population variance. And therefore, the sample standard deviation is going to be smaller than the population standard deviation. And it's based on sample size. So the bigger your sample size, the smaller the variability is going to be in your sample. So if you're using the sample that has less variability as an estimate for the population variance, you're going to make an error. So you're not going to have a really good measure because the sample tends to underestimate the population variance, especially with larger samples. You're going to underestimate the population variance. As a result, we need to correct for this. correct for this underestimating the population variance based on the sample variance. Now with the mean, the mean's gonna be fine. So the mean of many samples of a given size taken together, if you find the mean of those many samples you gather, and then you calculate the, compare it to the population mean, it's going to be the same in the long run. If you kept taking sample after sample after sample of a given size, and you calculated the mean of all those samples and compared it to the mean of the population, it's going to be the same. But the variance of those many, many samples is going to be less than the variance of the population. So this what's called biased estimate only affects the variance. It does not affect the mean, right? So the mean is fine in terms of extrapolating from the sample to the population. The mean is going to be okay. The variance is going to underestimate. The variance of the sample will underestimate the variance of the population. I know this is kind of abstract, and I don't expect you to really fully appreciate it, especially in the first course of statistics. And then secondly, you're taking the class online, which makes it, much more difficult to sort of follow up with the necessary clarifications and it's a much harder concept to do online than it is to do it in the classroom. But um, the bottom line is you need to know that the sample variance underestimates the population variance, and we must correct for that. We don't have to do that with the mean. Here's a image from your text that sort of shows this, that if you were to take samples, many, many samples, see all those X's there? Those are all your different samples you're taking from the population. You see how those samples are kind of clustered together? They're not that far apart. So when you're taking samples, there's not much variability in those samples you're taking compared to the whole population. See the whole population, that big curve, the normal curve? That's more spread out than all your samples are spread out from each other. And that's what I meant by the variability, the variance in the samples is going to be less than the variability in the population. So we have to correct for that. We don't want to just use the variability among our samples and say, okay, this is a good measure of what the variability is in the population. It's not. It's underestimating it. So we need to come up with a non-biased way of measuring the population variance. And that's what this picture is kind of depicting, that the sample variability is much less than you see in the population. The curve is much wider than the sample variability here. So how do we come up with an unbiased estimate if the sample variance is not doing a good job estimating the population variance? Well, what we do is we take our sum of squares, like I showed you before, and you divide it. Instead of dividing it by n to find the population variance, if I'm estimating the variance in a sample, I need to divide it by n minus 1. So if I'm calculating variance in a sample, take the sum of squares and divide it by n minus 1. If you're doing it in the population, take the sum of squares and divide by n. Now, realistically, you're never going to be doing this calculation in the population. So it's more of a theoretical point. You're never going to have access to the entire population. So if you have a sample and you want to calculate the variance of that sample, you're going to take the sum of squares and divide it by n minus 1. And you see the notation is different. So the variance of the sample is lowercase s squared. Whereas with the population, it was the Greek letter sigma squared. So that's how we denote a sample uses the actual letters, English letters, whereas the population parameters take Greek letters. So here variance is s squared, lowercase s squared. And then if I take the square root of the variance, I get the standard deviation of the sample, which is lowercase s. All I'm doing is taking the square root. So the n minus 1 here in the denominator leads to an unbiased estimate of the population variance. That's the correction I was mentioning. So now we are not underestimating it because we're dividing by n minus 1, and so we're making the variance bigger in the sample so that we don't underestimate the variance in the population. This is the correction. So in a sample, use n minus 1. In the population, use n. But in reality, you're not ever calculating the population variance in real life. So you're pretty much, in research, you're pretty much always using n minus 1. And the statistical programs out there will calculate using n minus 1. So SPSS and R, you could probably find the population variance if you wanted to, but I know that SPSS by default will use the n minus 1 formula because they realize you're not accessing the entire population in 99.999% of the time. We're not using SPSS because we don't have access to the lab this semester, but we're going to be using Excel, and there are ways to calculate the sample variance in Excel also that I'll be talking about next week when we do our Excel lab for descriptive stats. So this was just another picture of the histogram here showing that the average distance here, or the largest distance between the highest score and the mean here is 4.5, right? The mean is 6.5, the largest score is 11, so the distance there is 4.5, plus the distance between 6 and 6.5 is 0.5. So once again, the book gives you like a shortcut. So remember I said you could take 1/4 of the range to get you the ballpark estimate of the standard deviation. The book also talks about taking 1/2 of the distance between the largest score and the mean. Largest score being 11 here and the mean being 6.5. If you take half of that distance, you get a ballpark estimate of the standard deviation. That's okay as far as like just if you wanted to come up with an estimate, but most of the time you're going to actually compute the actual value the way I showed you how to do it. Now, in terms of the n minus 1 that I had just mentioned, this ties in with the concept of degrees of freedom. So in this situation, we need the population mean to actually calculate the population variance. And we get the population mean by computing the sample mean, because the sample mean is an unbiased estimator of the population mean. Do you have to know exactly what that means right now? No. The bottom line is that we're using the sample mean to estimate the population mean. And when we compute the sample mean, we know that the sample mean is equal to the population mean. So the sample mean is kind of set in terms of our inferential stats that we're doing. Using the sample mean restricts variability. And what does that mean by restricting variability? Well, go back to deviation scores. The deviation scores have to sum up to 0, right? So each score minus the mean must add up to 0. Therefore, if we know n minus 1 values in our sample, the last value is automatically fixed. And this is known as degrees of freedom. So that tells us in our sample, there's always going to be n minus 1 scores that are free to vary, and the last score is going to be fixed. It's not free to vary because we have to then calculate the deviation scores and they must sum up to 0. So once I've calculated all the deviation scores, that last deviation score can't vary because the sum of all those deviation scores have to sum up to 0. So that last deviation score is then fixed. And if that deviation score is fixed, then obviously the score, the actual raw score is fixed. I wouldn't go crazy about this concept. I'm telling you right now, this is an abstract concept. It's it's just a rule of thumb to try to explain the n minus 1, right? It's not that important yet. It will become more important when we do t-tests and ANOVA and things like that, where you're going to have degrees of freedom, calculate degrees of freedom. So the authors of the text have decided to now introduce it early on in this book, but introduce it very lightly. So I am not going to be holding you really responsible for degrees of freedom. You just need to know that in terms of the degrees of freedom, it's equal to n minus 1, because n minus 1 scores are free to vary. The last score is fixed. Uh, it's not, think of it this way. This is the way I try to explain it to people. Whenever you're estimating a population parameter based on a sample, you lose 1 degree of freedom. So if we're trying to estimate the population variance using the sample variance, I'm estimating 1 parameter, the population variance, using the sample variance, so therefore I'm losing 1 degree of freedom. If there's 2 variances, population variance I'm estimating, I'm going to lose 2 degrees of freedom. So that's kind of the rule of thumb. We always lose 1 degree of freedom for every parameter, the variance of the population we're estimating. In this case, we're only estimating 1 variance by computing the sample variance, and that's why we're using n minus 1 in the denominator, because that gives me the unbiased estimate. Is that kind of overkill for a course like this? Probably. But it's in the text, and I kind of wanted to mention it, and we can follow up with it, but it's not that important a concept other than knowing that it's n minus 1 right here. Theoretically, I wouldn't lose sleep over it. It's just kind of a procedural thing that has to be brought up. So here's our sample. We have 4 scores, and the sum of squares is 24. Now, SS is the sum of the squared deviations about the mean. So it's basically x minus the mean, each raw score minus the mean, square that difference, add them all up, and we get a total here of 24. So if our sum of squares is 24 and we have 4 scores, what is the variance of the sample? Well, remember, we're using n minus 1 for the sample, so it's going to be 24 divided by n minus 1, which is 4 minus 1, which is 3. 24 divided by 3 gives you 8. If this was population, we would use 4 in the denominator. But since this is a sample, I have to use 4 minus 1, or 3, in the denominator, so the answer is 8. And obviously, the answer is 8, because we're using n minus 1 here in the denominator. So just remember, sample n minus 1, population n. But most of the time, we're dealing with samples. Here's another check. Decide if the following are true or false. A sample systematically has less variability than the population. Well, I had mentioned that before, that the sample variance is smaller than the population variance. That's why we have to use n minus 1 in the denominator. So yeah, the sample has less variability than the population. It's true. The second statement, the standard deviation is the distance from the mean to the farthest point on the distribution curve. Well, no. It's the average deviation from each point to the mean, right? But it's not just the distance between the mean and the farthest score. It can be estimated using half of that distance as an estimate. So obviously the sample is less variable than the population, and the standard deviation is about halfway. So if you want to compute the standard deviation, you could take the halfway point between the mean and the most extreme score, and that's going to give you an approximation. Now, don't do that if you're asked to calculate the standard deviation. You want to do it numerically, right? You want to do the deviation scores and all that stuff. But if you wanted to estimate it, it's about half the distance between the mean and the most extreme score. Or if you want to also estimate it, it's 1/4 of the range. They're both going to give you numbers that are close, but not exact. And you should not be estimating unless it asks you to estimate. If it asks you to compute the standard deviation, You want to compute it numerically and not guess at it. So this is coming back to why the standard deviation of the sample needs to be over n minus 1. So the reason why we put the variance, I should say, over n minus 1 in the sample is because this produces the unbiased estimate. So this is the best estimate of the population variance, which I have talked about now for the last 15 or 20 minutes of the lecture, is n minus 1 in the sample gives us the best estimate, the unbiased estimate of the population variance. If we just use n in the sample, we are going to underestimate the population variance. And this is a table I just took from your text that shows you that if I'm dividing by n minus 1 versus n, you're going to see the unbiased estimate with n minus 1. And they just computed all the means from the sample. So each sample is 2 scores, and there's 9 samples, so they computed the mean. They computed the variance by dividing by n, where it says bias variance. That's the variance of those 2 scores divided by n. See, the first 2 scores of the first sample is 0 and 0, so the variance is 0. But you can see the difference in the second score, the second sample, where you have 0 and 3. And if you computed the mean of 1.5, the variance would be 1.5. So if the mean is 1.5, it would be 1.5 squared and then 1.5 squared divided by 2, which would give you 2.25. That would be the biased estimate, but in reality, the unbiased variance would be 4.5. So you see how that unbiased variance, in the case of having 2 scores in your sample, is double the biased variance. So the biased variance, the n in the denominator, so this is when you use the n to calculate the variance, it's underestimating it by half, right? It's underestimating the population variance by half here with a sample of 2. Now, obviously, you can use more than 2 in a sample, but you're going to still get the same results. You're going to have a severe underestimation of the population variance using n in the denominator, which is why we want to use n minus 1 for the sample. N minus 1 gives you this unbiased estimate of the variance. And you see that played out here. You can work this out on your own just to double check and see that the unbiased variance is far superior and it's a good estimate compared to the biased variance. Now we use means and standard deviations when we depict graphs. A lot of times we put them in journal articles, of course, but you can put them in a graph like the text does where they draw a line, a vertical line for the mean, and then a horizontal line for the standard deviation. That's useful for actually characterizing particular distributions. And you see that used throughout the text. The vertical line's in the middle, the horizontal line is to the side, and that denotes one standard deviation. And the 2 pictures here, you have the mean of 80 on the left, standard deviation of 8 in the population, and then you have the sample on the right here, where the mean is 16 and the standard deviation is 2. And that's useful to have the mean there depicting it. It helps you follow it a bit, right? It's just a graphical representation. Now, in a journal article, there's all kinds of things you can do in terms of showing variation. A lot of times they use something called error bars, which are confidence intervals around the mean. That's a little bit beyond what I want to talk about right now, but it's basically a measure of the variability that you see it. You see it in polling a lot where it has margin of error, where it says we have a margin of error between these 2 points. That's a confidence interval. That basically means that the true population mean lies between that confidence interval. We're not doing that right now, but that's kind of useful to show variability in a graph. So you see that a lot in journal articles. You don't really see the line and the vertical and the horizontal line that you see here, this is just the book showing you to try to help you understand these concepts. You will not see this in a journal article because it's assumed that if you're reading a journal article, you kind of know what the mean and the standard deviation is already. This is just to build your confidence interpreting these kind of scenarios with the mean and standard deviation. Now, can you do transformations to your data set, to your sample, and will that affect the population mean and standard deviation, or the sample mean and standard deviation, I should say? You could do it with the population as well, but most of the time we're doing a transformation to our sample. And if I add a constant, so if I add a number, the same number to all of my scores in my sample or my population, the mean is changed. So the mean is increased by whatever you added. Right, so if you add 5 to all your scores, the mean is going to be increased to 5. If you subtract 10 from all your scores, the mean is going to be decreased by 10. Common sense, right? The standard deviation does not change when you do that because the scores are still in the same relation to each other. You're just adding a constant or subtracting a constant. If, however, you multiply scores by a constant, then both the mean and the standard deviation do change. So if I multiply by 5, then the mean has to be multiplied by 5. And then the standard deviation is also multiplied by 5. So you multiply the standard deviation and the mean. If you multiply every score by a constant, same thing with division, you would divide the standard deviation and the mean. And then for addition and subtraction, you would change the mean, but it would have no effect on the standard deviation. So that's interesting to know. You could describe a distribution with just two numbers, the mean and the standard deviation. And in journal articles, you're going to see this all the time. So if you take, I teach a behavioral research course. If you take behavioral research, you're going to see this in the work assigned, or you're going to be reading articles and then trying to interpret uh, the take-home points of the articles. You're going to see the statistics part as well. And that's the first part I usually go to is the stats. I mean, that's kind of what I kind of focus on. I read the results section, I look at the stats, and I figure out what's going on. And then I'll read the discussion to see how they interpreted it. But it's very important to recognize things like means and standard deviations in journal articles. So that capital M in a journal article will represent the mean, and the lowercase s in the journal article will represent the standard deviation. And you'll see that constantly in the results section of journal articles. Here's a larger sample where they've calculated the standard deviation for you and the mean. So here we have 20 scores. Some of them are repeating. So this is your, the block histogram that you've seen before previously. And they calculated the mean to be 36 and the standard deviation to be 4. And as you can see, most of the scores in this graph are within one standard deviation above and one standard deviation below the mean. You see it here, the vast majority of scores are within plus or minus one standard deviation. And then as you go further away from the 4, the plus or minus 4, you get less and less scores. And that's what we would expect if the data are normally distributed. And this data looks approximately normal. You would need more data points for it to look, like a bell curve. But, you're getting something similar to a bell curve. It looks kind of flat in the middle, but I would expect that you would get more and more scores. If you increase the sample size, you'd get more and more scores in the middle of the distribution, and then you would get very few scores in the tail. So this kind of looks normal. The standard deviation is 4. And most of the scores in a normal distribution are going to fall close to the mean, especially between plus or minus 1 standard deviation. And you'll learn more about this in chapter 5 when we do z-scores and the normal curve. as I've been mentioning constantly, the goal of calculating all this stuff is to perform inferential stats. So we want to generalize from the sample to the population. That's why we're doing all of this stuff. I mean, you can calculate variance to describe your data set, but who really does this? I mean, I guess that's a preliminary step to doing your inferential stats, but it's not the main purpose of your research. The main purpose of your research is, gather your sample, test your project, do your manipulation, manipulate your independent variable, measure your dependent variable on your sample, and then draw conclusions about the population. In order to do that, you need to calculate the mean and the standard deviation and the variance, right? Those are very important for drawing conclusions about the population based on your sample, which is the goal of inferential stats. Now, as I mentioned before, you also want to have lower variability because when you have low variability, you're more likely to see patterns in the data or differences between subsets of the data that you're looking for in your research. When your variability is very high, it becomes very difficult to see the things that you expect to find because it's just a mess. There's data all over the place, and you don't know whether or not that the differences are really due to the effect of the independent variable you're manipulating, or they're due to just random chance. And that's the problem with a lot of variabilities. Is there really a difference between these two groups that I'm, manipulating? Or is it because there's so much variability that I can't really see the difference? So smaller amounts of variability are important for finding patterns and looking for differences that we're really looking at in terms of research. It's just easier to work with. When there's high amounts of variability, it becomes very hard to find what you're looking for. And variability is sometimes called error variance, and that's just basically variation due to chance. And when there's a lot of that variation due to chance, you have a really messy research situation and you can't find the differences in the data that you're really looking for. And as a result, you can't draw the conclusions that you want to. You can't support your research hypotheses. And here's a good picture of the high versus low variability. If you look at experiment A, you have low variability there, right? You see these two clustered groups, and they're separated by 5 points. So the blue and the, I don't know what color it is, beige colored blocks are separated by 5 points, and you can see that separation very clearly because the variability in those groups are very low. The variability in treatment 1 and treatment 2 are pretty low. They're all clustered together. Now let's look at experiment B. Now you have the same 5-point difference. But look at all the variability. Look at how spread out the blue bars and the beige bars are. They're spread out all over the place that you can't tell that there is a difference. But there is a difference here. The difference is 5 points between treatment 2 and treatment 1, but you can't see those 5 points. In experiment A, you see it very clearly. It's a picture perfect separation between those two groups. In experiment B, it's all over the place. So what's going to happen from a research perspective here is that in experiment A, you're going to be able to support your hypothesis and say that there's a difference between the groups. In experiment B, you're not going to because the variability is too big. There's so much going on here that you can't really support your research hypothesis because it's not clear. There's too much noise and not enough signal for you to draw a conclusion here. So you want to reduce variability like in experiment A. That gives you the clear picture of what you're looking for, and it helps you find the results more easily and support your hypotheses. So let's just do a rundown here. Quick check. A population has a mean of 6 and a standard deviation of 2. We're going to multiply each score by 10, so multiply everything by 10. What is the shape of the resulting distribution? Well, remember what we talked about. If we multiply every score by a constant, in this case 10, we have to multiply the mean and the standard deviation by the same constant. So we have to multiply the mean by 10, which gives us 60, and the standard deviation by 10, which gives us 20. So we're looking for a new mean of 60 and a new standard deviation of 20, and that's number C. And that's exactly what we find here. When you're multiplying every score by a constant, you must multiply the mean and the standard deviation by that same constant. And the same process applies to division. If I were to divide every score by 2, I would have to divide both the mean and the standard deviation by 2 as well. And let's look at this true-false question, the last slide for the chapter. A biased statistic has been influenced by researcher error. Obviously, that's not the case. A biased statistic is when you're not getting an accurate estimate when you go from a sample to a population, like we saw with the n-1 scenario in the sample. The n-1 is unbiased because it gives us an accurate estimate of the population variance. It has nothing to do with the researcher error. It's just a matter of, is it a good estimate or not a good estimate? Second question, on average, and so the first question has nothing to do with researcher error, it's false. The second one, on average, an unbiased sample statistic has the same value as the population parameter. Well, yeah, I mean, on average, an unbiased sample statistic, if it's unbiased, it's going to have the same value as the population parameter. That's why it's unbiased. That's why the mean of a sample is an unbiased estimator of the population mean, because if I took many different samples and found the mean of those many different samples, that would be equal to the population mean. And that's exactly what we're finding here. So hopefully this makes sense. It's going to probably be a work in progress because there's a lot of concepts here. I'm doing my best to explain the concepts through the lectures, but with the sort of separation, it's not as convenient as having a board to draw on or write on, and also having like sort of interaction in real time, and you're not getting that right now. So um, please read the text, listen to the lecture. If you have questions, send them to me. Practice. So the online homework is good practice. Sometimes there's a little glitch here or there with a question. These things happen with all these different software packages, but it's a good package. It's helpful. So do the problems, do the practice problems that you could do online too. They have plenty of options where you can actually work through step by step and compute the variance and standard deviation. So do those practice problems as well. Get out your pencil and paper and write everything down and start running through those problems. And start seeing if you can get the same answers as you get through the online practice problems that you can do. So every chapter there's online practice problems that you can keep over and over again, repeating either with the same numbers or different numbers and going step by step through it. And if you work through everything step by step, eventually you're going to get it. It's a matter of putting in the time though. And I think the online practice problems and the homeworks and stuff, that is a way of me forcing you to do the work. And you may not always like to do the work, or you may find it not, pointless, or you know it already, or whatever. It doesn't matter. I need to kind of force you to do the work and learn from this stuff, because I can't I can't just be there, force you to do the work, right? I mean, you have to kind of monitor yourself. And so please do the work, do the practice, do the homework. If you have questions, let me know. Come to my office hours, Mondays 2 to 4. Wednesdays 1 to 2. If you can't make those times, I could try to make additional times depending on my schedule. But those are the primary times that I want to really stick with. Come see me. I have the graphing tablet. I can try to work things out, do some stuff, with you in real time if you're on the Zoom. So we can also set up like a study session. So I'll let you know when I can do that next week. I'm not quite sure when I'm going to be able to do it outside of normal office hours. So when the exam comes, you'll have some more, feedback time or more communication time. So do all that stuff, practice on your own. I'll try to make myself available as much as I can. It's a tough situation, but we have to do the best with the whole situation going on in the world. So hopefully that's clear. Hope you enjoyed it. If you have any questions, let me know. Come to office hours email. I'm trying to get back as fast as possible to you. And I'll see you next week for Z-scores. Bye for now.